Good morning. I'll wait a little bit longer. Okay, I'm going to go ahead and get started. Hello, everyone. So I'm going to try to keep this pretty quick today because we have a lot to discuss in the Zoom room about going back to class on Monday. So yeah. So there is something that I forgot to discuss last time, and if you have already started the quiz, then Energy Production and Climate Change Quiz 2, then you may have encountered this on question 4. And that item is the topic of emissivity. So the emissivity is denoted by E, and it is between 0 and 1. Okay. And so if you have a perfect black body, then the Stefan Boltzmann Law says that the power is sigma a t to the fourth, where this is the surface area and this is the Stefan Boltzmann constant. So that is going to be 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. But not everything is a perfect black body, okay? So you can have, remember, perfect black body means that you absorb all electromagnetic radiation that hits you, okay? So you can see my forehead. This isn't the, so yeah, I'm emitting infrared light because I have a non-zero temperature, but the reason you can see my forehead is not because of the light my body is emitting, it's because of the light that is reflecting off of my forehead, okay? So, so what that means is that I could not be considered a perfect black body because that sounds really goofy to say, but that is because light, my forehead would absorb all light if it was a perfect black body. So if something is not or I'll just say non-perfect black body, then the Stefan Boltzmann law is unchanged, but we just multiply it by the emissivity. Okay, so so basically the emissivity is a number that you multiply into the Stefan Boltzmann law to take into account the fact that it is not a perfect black body. Okay, so that should help you answer question 4 on the quiz. So the next thing I want to talk about is what is called the solar constant. So the solar constant is the intensity of radiation from a star at your location. All right, so we already talked about this, so that's denoted by S. So really it's just an intensity. So an intensity is power per area. And we already talked about this in the context of solar panels. All right, so solar panels had a power output that was efficiency times solar constant times area. All right. Okay. So what if you want to calculate the solar constant? So let's suppose you have a star. Here's a star. Okay, and that star is emitting light. Okay, and here's an object that is being hit by that light, and so it is a distance d away from the star. Well, the solar constant is going to be the total power output of the star divided by 4 pi d squared. All right? So what we can see is that the further you are away from the star, d is in the denominator. So as d increases, the intensity of solar radiation goes down. The other factor that affects the solar constant is the power output of the star itself. Okay, the power output of so how much total energy is the star outputting per second? So I'm going to give you a couple of numbers here, and then we're going to calculate the solar constant that the Earth experiences. Okay, so all right. So the power output of the sun is 3.8 times 10 to the 26th watts. It's a huge amount of power, okay? So 10 to the 26th joules of energy per second. The distance between the Earth and the Sun is the distance between the Earth and the Sun is 1.5 times 10 to the 11th meters. And that is called 1 astronomical unit. So also known as an AU. So an AU is the distance between the Earth and the Sun. And that's a really, so actually both of these are frequently used in all over physics and astrophysics because it's a good scale. So you would not normally say that the power output of a star is, 9 times 10 to the 28th watts or something. You would say the power output of this star is 50 times that of the Sun. So we use the Sun as sort of the basis for comparing power outputs of stars. And then we also use the astronomical unit as the best measure of distance within a solar system. So for example, Neptune is 30 AU away from the Sun. Okay, so that means that it's 30 times the distance that Earth is. I believe Jupiter is 8 AU away from the Sun, and you can look up the other planets. Mercury is like 0.5 AU, or no, Mercury is like 0.3 AU. Venus is like 0.6. The Earth is, of course, 1 AU away from the Sun. Mars is like 1.5, I want to say. So there's all these different, okay, so let's go ahead and calculate what is the solar constant for Earth. Okay, so the solar constant for Earth would be 3.8 times 10 to the 26th watts divided by 4 pi 1.5 times 10 to the 11th squared. So let's plug that into the calculator. So this is the solar constant for Earth. Different planets in our solar system are going to have the same p-value, but they're going to have different distances from the Sun. If you're talking about an exoplanet that's in a different solar system, then it's going to have a different p-value as well, right? Because it's a completely different star. So I get 1,344 watts per meter squared. Okay. Now, if you remember, when I was talking about solar panels, I said that the solar constant was about 1,000. Okay. So why is there a difference between these two numbers? Well, as I said, the atmosphere actually absorbs some of the solar radiation. So the intensity of radiation at the bottom of the atmosphere is less. Okay? It's kind of like if you're in the swimming and you swim down deeper, the deeper you get, the darker it is, right? Because the water above you is absorbing that light. Exact same thing. The atmosphere is just like water in the sense that it's a fluid that absorbs light. It's just that the atmosphere is a lot more transparent than water is. Okay? So that is important. Whoa. So one thing I want to point out is that the power absorbed, so the power absorbed is going to be equal, okay, to the solar constant that the object experiences times the cross-sectional area of that object. And when I say the cross-sectional area, I mean the area that that object presents to the star. Okay? So let's say that this camera right here is the star. All right? I've got a book here. All right? So if I'm holding the book like this, all right, this area is the cross-sectional area. Okay? If I'm holding the book like this, so it depends on the orientation of the object. If I'm pointing this towards the camera, then this is going to be the cross-sectional area, this length times width, okay? If I'm holding it like this, then this is the cross-sectional area. So and then if I'm holding it like this, then it's like, this is like more complicated to calculate because it's whatever this projected area is. So I'm always going to have it so that like one of the faces is directly pointed at the star, so that it's just length times width. Okay. If you had a sheet of paper, all right, length times width, that's the cross-sectional area. But if I turn the piece of paper like this, try and get it exactly right, so that it's completely edge on, then that would mean that the cross-sectional area is 0, all right, because the light just kind of like passes by. This is not the edge of a piece of paper is a very small target. If you have a spherical object, I gotta find a ball here. Give me a second. A ball is obviously spherical, and so its cross-sectional area is the area of this circle. So it's going to be pi r squared for a sphere. Okay. If you have this frisbee, this is kind of interesting because it depends on how it's oriented. So if it's like this, it's going to be width times length. But if the frisbee is like this, the cross-sectional area is pi r squared. Okay? So it depends on the orientations of the objects when you're getting the cross-sectional area. All right. And so there is one more fudge factor, okay, which is okay, there is one more fudge factor, which is for the albedo. Hang on, I got a weird scent. What are you doing, Bugs? So remember, albedo is the fraction of incoming light that is reflected. So 1 minus the albedo is the fraction absorbed. So, yeah, this is an important equation for today. Okay. Now, one of the cool things that we can do here, all right, is we can calculate the equilibrium temperature. Okay. Calculating the equilibrium temperature. And so here's the idea. Whoa, we got a doggy fart happening. you have a planet. Let's say you have a planet. All right. So it's a spherical object because planets are so large that gravity compacts them into a sphere, approximately a sphere. And that planet is absorbing light from a star. So there's a star that's like over this way. Okay. Now some of that light is being reflected. That's the effect of albedo. Okay. So maybe some of these are reflected, but most are being absorbed. Okay. Now in response to that, the planet, because it's absorbing some of that light, it's absorbing energy. Okay, so it's going to heat up. And as it heats up, from the Stefan Boltzmann Law, we know that it's going to begin to emit its own light. Okay, so the planet itself is going to start emitting probably infrared light into outer space. Okay, so here's reflected. Here is emitted, and these are some of the absorbed photons. Okay, now here's the key observation. Okay, at equilibrium, so equilibrium means that the temperature on average is not changing. Okay, at equilibrium, the power that is being absorbed has to be equal to the power that is emitted. All right. The power that is absorbed has to be equal to the power that is emitted. What would happen if the power absorbed became greater than the power emitted? Well, in that case, you have more energy coming in than is going out, so the temperature is going to rise. And as the temperature rises, according to the Stefan Boltzmann Law, it starts to emit more power. Okay? If the power absorbed is less than the power emitted, then the temperature is going to drop. And so until the power emitted matches the power absorbed. Okay, so at equilibrium, these temperatures are in balance. If they're out of balance, then the temperature of the planet is going to start to change. Okay. Now, because the temperature, and when I say the temperature, I mean sort of like the average global temperature. Okay. Because the average global temperature is changing, but it's changing very slowly. This is more or less true. Okay. So now what we do is we go, all right, the power absorbed is, okay, the power absorbed is what I just talked about. So 1 minus alpha times the solar constant times the cross-sectional area. So I'll just call that A sub x. The power emitted comes from the Stefan Boltzmann Law, and we're assuming that it's not a perfect black body, so it's emissivity times sigma times A times T to the fourth. And I want to point out that this is the surface area, okay? Because it's emitting from the backside of the star as well. So the surface area of a sphere is 4 pi r squared. Okay. If we had a book, okay, the surface area of a book is going to be this face plus 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 this face. So there are 6 faces in this case. All right. So there's a difference between surface area and area that you're presenting to the star. So that is important. And so then we divide. So notice how it depends on the ratio of the cross-sectional to the surface area. And that's going to be t to the that's going to be t to the 4th equal to t to the 4th power. So we have to take the 4th root of it. So we go to the 1/4 power. All right. So if you don't know how to do the 1/4 power, that means raise it to the 0.25 power. Okay. And so this is the equilibrium temperature of the object. All right. So we can actually predict the equilibrium temperature of stars, or of planets, excuse me. And we can see that as we move further, as the planet moves further away from the star, the solar constant is going to go down, which is going to reduce the equilibrium temperature. All right. So, one of the things that I read a book, was it last summer or at some point I read a book on astrobiology, and there is a term kind of called the Goldilocks zone. And it is equal to the range of distances where the equilibrium temperature is less than 100 degrees Celsius and greater than 0 degrees Celsius. Okay? So that means that the planet could have liquid water on its surface. Okay? So Earth happens to be sort of right in the middle of the Goldilocks zone for the sun. Okay? And I think Mars is the sort of on the outer edge of the Goldilocks zone. So what that means is that Mars could have liquid water, depending on its albedo and emissivity. Now, I don't think it does have liquid water on its surface because its albedo is maybe too great. The emissivity is strongly affected by the atmosphere, and so the emissivity of Mars, because Mars has such a thin atmosphere, is going to be, it kind of behaves more like a bigger emissivity. Okay. The smaller your emissivity is, the more heat you're retaining. So the thicker the atmosphere, the smaller the emissivity. So let's go ahead and calculate this for the Earth. So assuming Earth is a perfect black body, okay? Assuming Earth is a perfect black body, well, that means that the albedo, it's not reflecting anything. So the albedo is 0. It means that the emissivity is 1, because I said that, see how for a perfect black body, it's the same equation, but if we set E equal to 1, okay? The Earth is a spherical, okay? So if we look at cross-sectional area divided by surface area. The cross-sectional area is pi r squared, but the surface area is 4 pi r squared. So that means that the cross-sectional area divided by the surface area is 1/4. All right, so plugging that information here. Oh, and by the way, we just calculated that the solar constant was 1344. All right, so I'm not using the 1000 number because, you know, the atmosphere is part of the Earth, so we want to use the solar constant that the entire Earth experiences, not at a certain depth inside the Earth. Okay, so, and this is in watts per meter squared. This cat is going crazy. So I went into school yesterday. Wow, wow. I went into school yesterday. He's so used to going outside and playing in the backyard while I'm teaching. And then yesterday I went into school, so he couldn't go outside. And he just has been having a mental breakdown ever since. He's just like walking around meowing. Can you guys hear that? Wow, wow, wow. And then he's like whacking the dogs. He has like so much attitude right now because he can't go outside. It's pretty funny. Okay, so we have 1 minus 0, which is just 1. Then we have 1344. The emissivity is also 1. Stefan Boltzmann constant is 5.67 times 10 to the negative 8. Cross-sectional area divided by surface area is 1/4. Okay. So, if I do that, I have to take the 1/4 power. I get 277 Kelvin. Okay? This is assuming the Earth is a perfect black body. Okay? And so that's pretty cold, right? Because the freezing temperature of water is 273 Kelvin. So this is basically entire Earth is almost frozen. So what gives? Why aren't we getting something nice like 300 Kelvin? That 300 Kelvin is closer to the actual surface temperature. Well, the reason is that the Earth is not a perfect black body. Okay, it has an albedo, it has an emissivity. Okay. Now, as I said, the emissivity is sort of controlled by the atmosphere. All right. And the albedo is kind of controlled by stuff on the surface. Okay. So if we talk about climate change, basically what's happening is because of the things that we are doing to the planet, we are pumping, fossil fuels, carbon dioxide, etc., greenhouse gases into the atmosphere. That's making the atmosphere capture more of the radiation that the Earth is emitting. Okay, so it's reducing the emissivity. So by pumping fossil fuel, we are reducing the emissivity, which causes the equilibrium temperature to go up. Okay, but then there's a second effect, which is really sort of pernicious, which is that as the temperature rises, ice on the surface will start to melt. Now, what does ice melting do? Well, ice reflects sunlight. So the more sunlight the Earth reflects, the cooler the Earth is going to be. So if ice melts, then the Earth reflects less sunlight, which means it absorbs more. Okay? So basically, there's a double whammy effect, right? We pump carbon dioxide, we pump greenhouse gases into the atmosphere, the emissivity goes down, ice melts, which makes our albedo change so that we absorb more, which makes it so it's called a positive feedback loop. Okay, so we have to be really careful that we don't. There's sort of a range of temperatures where the Earth is able to sort of maintain itself. Okay, so negative feedback means that if you go away from equilibrium, there are changes that take place that push you back into the center. Okay, positive feedback means that if you go away from the center, then forces come into play that push you further away from the center. So positive feedback is like an out of control situation. Negative feedback is, means that the system sort of naturally stabilizes itself. So, when scientists are saying like, we could be reaching the point of no return, what they mean is that we could be getting to the point where we start to enter a positive feedback loop, in which case the temperature is going to get out of control. Okay. So yeah, so that's how this all connects to climate change. I'm going to talk more about it in the Zoom room, but I think I'm going to stop the lesson there. So I will see you in the Zoom room.